Hello everyone and welcome to Radioactivity with Vodka. This is my lab setup here. We have the Geiger counter right here, courtesy of James Warner, ordered from China and custom assembled. That's hooked up to the battery pack, and this is our distance scale. And right here is an orange Fiestaware plate. This orange Fiestaware plate, in the dyes and glaze used to make it, contains uranium oxide in the form of uranium-238. When we switch on the Geiger counter and move the plate closer, it'll do something like this. Detecting radiation given off by the plate. But there are multiple different kinds of radiation. There's alpha particles, gamma particles, and beta particles. This plate actually gives off all three. Before we begin talking about the actual lab, it's important to understand what is happening when I say that the plate is giving off radioactivity or giving off radiation. Thank you, Mr. Fudge, for letting us borrow a couple of his old Fiestaware plates. We are using the orange one because the red dyes that Fiestaware used to use contained uranium oxide, which contained uranium-238. And as uranium-238 decays, it decays into thorium-234, giving off beta and gamma radiation, and thorium-234 has a half-life of about 2 weeks. So that's pretty unstable, and then the thorium will decay into either protactinium-234 or uranium-234. And if it decays into protactinium, it will give off beta and gamma radiation. And if it decays into uranium, it will give off alpha and gamma radiation. Starting off with alpha particles. Alpha particles are the type of radiation that it's the most harmful, but it's also the least harmful. What I mean by that is alpha particles are very dangerous and very toxic and absolutely destroy living tissue, but they also have next to no ability to go through any sort of barrier whatsoever. So alpha particles very seldom make it through human skin, and so the only way you would have a problem with alpha particles is if you ingested some. So alpha particles are emitted during alpha decay, and they look astonishingly like helium atoms. They have no electrons, so it's just 2 protons and 2 neutrons, and so it's just a +2 helium atom, except it's emitted during radioactive decay. It is the most common type of radiation, and the little black box in the lower corner is an actual picture of the trace left by an alpha particle. Next up are beta particles, which have the same mass and charge as an electron, and they're often produced in conjunction with alpha particles. So we said earlier that the alpha particles look like a +2 helium atom, and so they don't have any electrons, and this is where the electrons come from, the beta particles of radiation. And it has the same mass and charge as an electron. Beta particles pose a medium level risk to tissue, and they also pose a medium threat as to getting through protections. So they'll get through some light protection, like say maybe tinfoil, but not through heavier protection, such as anything thicker. And their beta particles are the more dangerous of the particulate radiation. And when I say particulate, I mean that they are in the form of a particle, and gamma radiation actually is not. Gamma rays were originally thought to be particular in form like alpha and beta radiation. They were discovered most recently. They're actually the shortest type of electromagnetic wave. So the electromagnetic EM wave spectrum runs all the way from AM radio on one end to gamma rays on the other. and visible light is somewhere in the middle, so is UV light. Gamma rays have the shortest wavelength and can penetrate most objects because of that short wavelength. Most radiation protections are ineffective against gamma rays. However, they also pose a relatively low risk of tissue damage, and you have to be exposed for a long time for it to cause any damage. I'm sorry, Hulk is not realistic. E equals mc squared is probably the most famous scientific equation. It's talking about the mass energy equivalence. So an alpha particle is made up of 2 neutrons and 2 protons that make it up, right? Right. But an alpha particle is lighter than the 2 neutrons and the 2 protons that make it up. The difference is called the mass defect, and it can be translated into an energy difference by multiplying the mass times c squared. C squared is the speed of light squared. And so this is a tiny part of the energy of an alpha particle, but when you get a lot of them, it starts to build up quickly because the energy is equal to the mass, which in this case is very small, but that's multiplied by the speed of light squared, which is a huge coefficient. So a small amount of mass breaking down, say a couple grams of uranium in a nuclear bomb, releases a ton of energy because it is the mass in just a couple grams is being multiplied by the speed of light squared. The rate of radioactive decay is the same as a first-order kinetic reaction. It is concentration of A is equal to the beginning of concentration of A times e to the negative kt, where t is time and k is the decay constant. And it basically just looks like your basic exponential decay graph. K is the decay constant and can be found by rearranging the original equation. So you get something that looks like this, and the decay constant is necessary to find the concentration remaining of the substance at any given time. And this can actually also be used to find the half-life if you set the concentration of A to half of the original concentration. So I took all of the data regarding distance. I had the plate 1 meter away, then 75 centimeters, and 50 centimeters, and then 25 and 20. And it was interesting to see the exponential rate at which distance affected the amount of clicks and the amount of radiation absorbed by the Geiger counter. And I'll have that information up in a second. This is the data converted to microsieverts, which is the unit used for radiation. Please note that this is converted before I applied the correction for background radiation. I measured total number of clicks and then didn't subtract the number of clicks just from the ambient background radiation to begin with. And the power B, which we had expected to be around -2 for the 1 over x to the squared graph, the radical graph, we got 1.12, which is not close. But then once I applied the subtraction to fix the ratio between the ambient and plate generated radiation, then it fixed it, and the exponent was -1.99. So within a deviation, pretty close. And that fixed any problems we had in the data and predict. After I finished taking the data regarding distance, I decided to experiment with different forms of physical protection against radiation. Distance might be the best one. You're separating yourself from radiation entirely, but if you do have to come in contact with radiation, there's a couple different ways that you could protect yourself from it. So we've placed the uranium plate 5 centimeters away from the Geiger counter, and just listen for the clicks for a second. That's probably about 1.5 microsieverts of radiation being absorbed. So now we're going to wrap it in this napkin that Mr. Fudge gave us, and we're going to see what happens. So I've taken it away, so it's less now, but then we're going to put it back at the same distance. And it's still going pretty good, but it's definitely a lot less. So I'll unwrap it again. You can see, listen to the difference. It's quite a big difference just from one piece of cloth. So let's try something else next. So now we have a very dense object, this chemistry textbook, and we're going to put it in between the Geiger counter and the plate and listen for the difference. It stops completely when we put the book in between. And so what that tells us is that the plate is actually not emitting very many gamma rays. It's mostly alpha and beta particulate radiation. Because gamma radiation should, in theory, be able to penetrate one chemistry textbook. And it doesn't, so we can safely assume then that the plate is giving off mostly alpha and beta particles. Now we're going to try with a NASA magazine that I randomly found in Mr. Moser's classroom. I'm going to slide that in between and listen for a difference. So you can definitely still hear the clicks, but it's for sure a lot less. The multiple layers of the paper are absorbing a lot. That's probably blocking most of the alpha radiation, and there's what's left getting through is the beta particles. Thanks for watching, everyone, and I hope you learned a little bit about radioactive decay and radiation and better ways to protect ourselves from the harmful effects.